To produce hydrogen cyanide, we need short wavelength photons in the UVC range. To produce ribose, we need long wavelength photons in the UVC range. To produce photochemical dissipative structuring, we need long wavelength UVC photons. Phosphorylation, also long wavelength UVC photons. And to get this temperature and UV assisted reproduction, we also need long wavelength UVC photons, which I talked about on a different slide or different talk, actually. And we also need high temperature and also variation of the temperature during day and night to allow this process, like the PCR process of replication. But this is a PCR process augmented by the absorption and dissipation of photons. That increases, if you like, the temperature locally. We really think now that it's charge transfer, which is occurring, which is changing the charge densities, distribution of the charges on the basis, which is allowing them to separate, to break the hydrogen bonds. Okay, we also need proliferation. I haven't talked about that yet. I'm going to give that in another talk, but that also requires photons in a long wavelength UVC range. So just briefly, this is making an analogy with a chemical reaction. So this chemical reaction is A going to B through an intermediate, which is X. And then X produces another intermediate, which we call M, which acts as a catalyst for A going to X. So you can imagine that if this is a catalyst, it's going to speed up this reaction. So if we have a source of A and an output of B in the environment, then with this greater amount of catalyst, we're going to get this reaction going much faster. So we're going to get more catalyst. And so this is an autocatalytic system. And you can imagine that the quantity of the catalyst M is going to increase over time very quickly. That is like proliferation. And it's the same thing which is happening here in this UV tar process. But as I mentioned, we'll get into that into more detail in the following day, maybe in the next class. We also need homochirality, that is the selection of certain chiralities. Because if they're mixed chirality, which is the most natural occurrence for abiotic production of these molecules, if we have mixed chirality, then we don't get extension. You cannot build a second DNA structure on the backbone of the first single-strand DNA. And that homochirality also comes from UVC light at the surface, which can be circularly polarized. And we'll talk about that also in another talk on a later day. And also for evolution, as I mentioned, the connection of tryptophan to DNA can be considered like a form of evolution, because now the information is being stored into DNA to make it a better dissipative system. And what we don't want is this medium wavelength UVC, which is below about 180 nanometers, which could cause ionization and therefore the destruction of these particles. So we don't want that on the surface. Well, of course, we don't also want the very short wavelength UVC because that on the surface, because that could also destroy the molecule. We do want it in the atmosphere to be able to provide hydrogen cyanide, for instance. So as you saw in the first graph, there are different types of stars, M-type stars, which are these red stars. These are two different variants of M-type stars. And then we have K-type stars. And then we go to the G-type, which is our sun. Okay, this is the spectrum of our sun, the same spectrum I showed earlier. This is the little peak in the yellow here. This is a little peak in the UVC range. And then we go to F-type stars and then A-type stars. And there's also B-type star, which we don't include here because it has too much energy here, too much intensity in this range, sorry, in the medium UVC range. So that will be destroying very easily the atmosphere of, well, the important molecules on the surface better than the atmosphere. But also with the short wavelength UVC light, it could be destroying molecules in the atmosphere. And so we're looking at these basic stars. This is assuming that we have a planet similar to Earth, which had the same gases as Earth had at the origin of life. So we have these aldehydes absorbing in the atmosphere, and we have CO2 and maybe some hydrogen cyanide absorbing. And then we look at the intensities. So this is the long wavelength UVC region. This is a good region. That's what we want for dissipative structuring. We want that on the surface. We don't want medium wavelength UVC light on the surface, because that can do the ionization and destroy the molecule. And we also don't want short wavelength UVC light on the surface, because that can destroy it even faster. But we do want short wavelength UVC light in the atmosphere, so that we can produce these precursor molecules like hydrogen cyanide. So this is the spectrum, assuming that the planet has atmosphere like Earth's early atmosphere for different star types. And these are the, assuming that, well, this is the spectrum at the top of the atmosphere of these same stars. Okay, so what we can do then is integrate for these different types of stars the amount of energy in each of these regions, in the short wavelength UVC range, medium wavelength UVC range, and the long wavelength UVC range. We just integrate to find out the total intensity and how the intensities varies as a function of star type. So we have plotted that in this graph. And so these are the star types, M, K, and G type, F, and A. And these are the surface temperatures, the average surface temperatures of those types of stars. And this is the distance that a planet like Earth would have to be from the star in order to have liquid water on the surface. So for example, in the M-type stars, this is in astronomical units, the planet like Earth would have to be very close to the star. And for our sun, well, it's at, the Earth is at 1 astronomical unit. For these other stars, it would have to be further away. Otherwise, we would have water being a gas, being evaporated. So what we're trying to do is keeping more or less the total energy flux over the whole region of the spectrum the same for these different stars. That's how we determine these distances that the planet had to be. So this is the flux of energy per meter squared per second for these different star types for planets like Earth at these distances. So that basically we keep that constant, so we have liquid water. And then we integrate over the long wavelength UVC region. So that's just integrating over this region here. And that gives us these energy values. So these are good energy values. These do the dissipative structuring and the proliferation and so on. And we also integrate the medium wavelength UVC range at the surface again. This is this range here, which can cause ionization. And then we do the short wavelength UVC range, which we do want, but only in the upper atmosphere, not on the surface. Okay, and that gives us these values integrated over this region of the spectrum. So just to remind you then that we want long wavelength UVC light on the surface. We don't want medium wavelength UVC light on the surface because of the ionization. Remember, this is the ionization spectrum. So anything below, actually here, we should put really 180 nanometers. Anything below 180 nanometers, we don't want. And, but we do want short wavelength UVC light in the upper atmosphere to producing hydrogen cyanide and to get these other molecules from hydrogen cyanide. So then we can rather calculate an equation for the probability of life arising on a star of a particular type. So we have these three different regions, fluxes of energy in the long wavelength, medium wavelength, and short wavelength UVC ranges. So to calculate the probability, well, we know that long wavelength UVC light is good. So we could raise this concentration or the intensity to a certain power L, which could be equal to the number of independent dissipative structuring, proliferation, or evolution processes. And in fact, there are assays. So we take that to the power of 6. And for M, we don't want, so we take a negative power, and there's only one independent process, which is negative, which is ionization, destruction of the molecule. So we put that concentration to the -1. And then we have number of independent processes of dissipative structuring in the upper atmosphere, which is 1. So we can form a probability, and we can argue about this and criticize it. It's not actually a very well thought out, did it rather quickly. So it can, of course, be criticized, but we can kind of form a probability or expectation value of life on the different star types, depending on the concentrations or the intensities of the different lights in different regions, and the number of processes which are dependent on that kind of light. And then we can also multiply it by the age, the maximum age of the star. Because, for example, if we want to know if we have evolution like is occurring on Earth to get into complex ecosystems, well, we need apparently about 4.5, well, at least 3.85 thousand million years to get to our complexity of the ecosystems. For example, for looking for the biosignatures. So we can form a probability and see as some kind of a constant, a proportionality constant. And then we plot these on a graph of star type. So this is temperature, if you like, of the surface of the star. And this is the probability of finding life as given by this equation. So we put the probability for finding life on G-type stars of equal to 1. And then look what this probability gives for other stars, other star types. And we find, for example, for F-type stars, it gives 1 times 10 to the 3. And for A-type stars, 7 times 10 to the 3. But we have to be careful here because we're considering age also for evolution. So even though this gives us greater probability of finding life on F and A-type stars, we have to take into account that stars have a certain lifetime. A-type stars, for instance, exist for only about 370 million years, and F-type stars for 3 billion years. In our sun, well, it's already lasted for about 5 billion years and may last for another 5 billion years, but average age would be about 5 billion, and for K-type stars, about 10 billion. So, for example, on A-type stars, even though the probability of getting life or finding life may be high, it has a very short lifetime, only 370 million years. So we might be lucky if we find bacteria on a planet of such a star. For F-type stars with 3 billion life years, if evolution is similar to our own on Earth, then we could expect plants and maybe even some sea animals after about 3 billion years since the origin of life. But for example, get to intelligence, technological intelligence like we have on Earth, That would take at least 3.85 thousand million years. These other stars are more long-lived. The K-type stars live for 10 billion years. But the probability of finding life by this formula is very low. And that's because there's very little light in the long wavelength UVC range. So we can assume that probably, if anything at all exists, we would have just some of the precursors and maybe some of the fundamental molecules, but not all of them, and not process of life. So these are two different M-type stars, which are these red stars. AD Leo is a star which they're focusing their attention on, and it will be looked at with the James Webb Telescope. They're looking for life on the planet's biosignatures. But according to us, because it has almost no or very little UVC light in a continuous form, it does have outbursts. For example, they know that these red type stars have a lot of outbursts. That means that all of a sudden they can become very hot and emit, well, at least in regions of the star, ultraviolet light in the UVC range. But they're only for brief periods and they're not continuous. So according to us, it would be very unlikely to find life like we know it on those stars. So we could say, and we should write a paper saying that they're going to be wasting a lot of time, or they could be wasting a lot of time, because we're not 100% sure about our theory, but could be wasting a lot of time using the James Webb Telescope to look for biosignatures on red type stars. Surely they will find some, for example, methane, but methane can be produced through other processes. You know, it can come from volcanoes, or it can be produced through this serpentinization process, which is essentially hydrolysis of other molecules over rocks. So they could find some biosignatures, but it's very doubtful that they would be related to the origin of life. It would be like on Mars, they found methane, and they're wondering, no, is this related to life or this is not? And now they have basically determined that the methane they have found on Mars is probably produced by some abiotic process and not by life. So that the same thing may happen on these M-type stars, that they find signatures which say, oh, okay, maybe there is some life here, but we're not sure, and that will go on for many years. No? But I think it would be better if we could convince the community to study G-type stars and planets on G-type stars, even though those stars are much more difficult to determine because of their size is much greater and the intensity of light they emit is much greater, and the distance of the planet from the star has to be much greater. So we're going to be finding it, looking at it as a small planet in front of a very big bright star, which would be very difficult to do, but that is where probably life would be found. Now there's also other problems with M-type stars, for example, their magnetic shield. On the planet, M-type stars, as I said, have these outbursts of charged particles and UV light, and that could erode away the atmospheres. So the planet would need a very large magnetic shield in order to protect the atmosphere from the erosion due to the particles emitted by these M-type stars. Also, to get liquid water on the surface, we need about 500 watts per meter square. And this is important for hydrogen bonding and dissipated medium for dissipating the electronic excitation energy. So the M-type stars, for these stars, the planet would have to be located very close to the star itself. And that would mean tidal locking, like what has happened between the moon and the Earth. You know, we see only one side of the moon because it's tidally locked with the Earth. So its rotation on its axis is exactly equal to its revolution time around the Earth. And the same will happen with these M-type stars and their planets. Planets which could harbor life would have to be very close in order to get liquid water. That would mean that there could be tidal locking and therefore no no day and night occurring. So, and also on the daytime, the temperatures will be very high. And on the night side, the temperatures will be too low. So we wouldn't get this ultraviolet and temperature-assisted reproduction process occurring. So yeah, basically that is all I wanted to say, just in conclusion then. So we need short wavelength UVC light in the upper atmosphere for dissipative structuring of hydrogen cyanide. Medium wavelength we don't want on the surface because this could ionize the fundamental molecules. We need long wavelength UVC light on the surface for dissipative structuring and for proliferation, for homochirality, and for evolution. We need also high surface temperatures. So we get a temperature of close to the DNA denaturing temperature and decreasing slowly through time. And we also apparently need a diurnal temperature cycling, which is the question that Esmeralda asked at the beginning of the talk. So we probably need this diurnal temperature cycling, but exactly how long day and nights have to be, we don't know that yet. And so therefore the stars which are suitable for the origin of life are only G-type and F-type stars. But stars not suitable would be these harder stars, O, B, and A-type stars. And so, and neither would be these K and M-type stars, because they would be these red stars which have the problem of the tidal locking and no UVC light. And it turns out that these stars, in which we wouldn't expect life like our own, make up the majority of stars in our galaxy, about 90%. So only 10% of the stars in our galaxy could have life like our own. And so the biosignatures that we could look for example, would be oxygen, ozone, and methane, chlorophyll, etc., other pigments, but only on G and F type stars. Now we could have life on these K and M type stars through a process known as panspermia. So once you have a developed system like a bacteria and a spore, then these spores can be translated through space, and they've determined this through experiments on spacecraft. And we could have what is known as panspermia, and that could give rise to life on these K and M type stars. If life was formed on G and F type stars and later transported, for example, by an impact of a meteorite, like we found meteorites on Mars through impacts of pieces of meteorite on Mars on Earth from the impact on Mars, then we could have transportation, this local panspermia. And this was first suggested by Hoyle and Wick-Ramasinghe. And so we could have life on planets of K and M type stars, but only unless we have panspermia. Okay, are there any questions? Esmeralda?
Entonces, cada organismo evolucionaría como todo este ADN que le dice cómo disipar, evolucionaría hasta poder disipar el máximo de VC y ya lo han tratado de mandar a alguien que esté viendo lo del James Webb o algo así, porque si es un desperdicio de tiempo, pues sería bueno que lo consideraran.
Yeah, well, we haven't written the article yet, you know, to be considered by these professionals on these very costly telescopes. One has to produce a very well-written article and be convincing. And right now, unfortunately, it's not going to be easy to convince them because they are astrobiologists who are basically following the Darwinists, and they don't consider dissipation into account. So I think we would have a hard time convincing them not to. But it's worth writing the article. We just haven't had time. We've having too many other interesting lines of investigation. But it would be a very good idea to try to produce an article and get it published, and then maybe they would start looking at it. Maybe we can do that in the next 1 or 2 years. The James Webb Telescope will be operating for at least 10 years, like Hubble Telescope has been operating now for more than 20 years, I think. So we're still in time, but somebody has to sit down and do it, and it's a lot of work really to produce a good article that can be convincing. So,
¿Y podríamos ayudarles? Digo, bueno, de mi parte, no creo saber muy bien cómo escribir artículos, pero si pudiera ayudarles en cualquier cosa, pues estaría súper padre. Digo, no sé si los demás quieran, pero estaría bien.
excelente. Sí, no, excelente. Si quieres colaborar, si encuentran algo interesante que quieres colaborar conmigo, no hay problema. Ahorita es un poco difícil con las becas, pero si tienes, por ejemplo, beca de CONACYT, which Ivan has, then it will be much easier. It's not so easy to get becas. We have to put in projects and they take a lot of time and all that. What is your thesis project now? Do you have something, Esmeralda?
No, porque, bueno, estoy en sexto, jaja, pero últimamente había pensado que me gusta mucho la termodinámica, entonces tal vez me gustaría orientarme a eso. Como todavía no he llevado cuántica y me gusta, y cosmología y eso, no estoy segura, pero pues me gusta mucho la termodinámica. Entonces,
Sí.
aunque no fuera de tesis ni nada, pues me gustaría apoyarlos. Y si fuera de tesis, pues estaría genial.
Sí, sí, bueno, apoyar, dices, ¿no? Como colaborar de una manera. No en
Sí,
un thesis quizás, pero en un artículo. Pues eso
sí, también
depende,
me parece.
depende de ti, porque creo que los estudiantes tienen muy poco tiempo, ¿no? Y normalmente si están haciendo la tesis con otro asesor, es difícil que los dejan tiempo suficiente para colaborar con alguien más. Es que ya a los últimos años yo creo que son los más pesados por la cantidad de trabajo, ¿no? Escribiendo la tesis. Aunque también hay otras opciones, ahorita puede publicar un artículo y graduarse con este artículo publicado. Es otra manera de graduarse. Pero sí, depende del estudiante, depende de ti, los tiempos. Ese es
Ok,
el
ok.
problema, que el tiempo es el recurso más importante en nuestras vidas y no nos damos cuenta hasta que ya estamos casi por morir, ¿no? Pero es por mucho el recurso más valioso.
Sí, sí,
Sí.
pues lo voy a ver porque desde que vi el tema de la clase, pues me ha gustado bastante. Y también estaba leyendo este librito de como termodinámica en, no, no es cierto, física en distintas ramitas y así, que escribió para ver lo de las intersecciones cónicas. Y dije, wow, eso está bien padre. Y el siguiente artículo
Ajá.
también era de la vida y como la explicación termodinámica en
Sí,
otros planetas. Y también dije, wow, esto también está bien padre y lo vimos allá. Sí,
sí,
está muy bonito.
sí, es un área muy padre. Sí, pues bienvenidos si tienen tiempo, pero depende más de ustedes y sus asesores. Pero yo con mucho gusto. ¿Otras preguntas? Esmeralda o otros? ¿No? Entonces yo creo que lo terminamos la clase de hoy. Y nos vemos entonces en una semana. No verán sus tareas, no estoy viendo, llegando tareas de ustedes. ¿Sí están haciendo sus tareas, Esmeralda?
Sí, de hecho, esta Bueno, es que la 3 se quedó ahí y estaba terminando la 4, entonces quería mandar la 3 y la 4 hoy. Ujú.
Ok, ok, excelente. Bueno, entonces voy a intentar a salir de aquí. No me está dejando. Aquí está. Entonces voy a finalizar y nos vemos en una semana entonces. Cuídense mucho. Hasta luego.
Igual, profesor.
Hasta luego, Iván. Y luego lo comunicamos, Iván, por email.
Sí, nos
Ahorita
vemos.
voy a ver eso.
Gracias, hasta luego.
Ok, hasta luego.